Attila Szegedi of Microsoft.
Thank you very much. This has to be the nicest introduction I got ever, and I'm sure it made me blush. So welcome everybody to the talk about real-time tweet delivery architecture at Twitter. You were supposed to have Rafi standing here. Rafi is an ex-colleague of mine. He is Director of Platform Services at Twitter, and he's unfortunately unable to be here, but he is here with us on Skype. Say hello, Rafi.
Hello, everybody. I'm sorry I couldn't make it in person.
Right, excellent. But he'll be here. He is probably better qualified to answer the questions, and he's of course free to chime in anytime I leave something out or maybe get something wrong. The reason I'm standing here in front of you is I'm currently with Oracle instead of Microsoft, and I'm here at the Stockholm office, so I was at hand as a substitution. So I did actually work for Twitter before for about 2 years before I joined Oracle, and I was working in a runtime systems team that's closely working with Rafi's team, and so as luck has it, I did actually work on mostly performance tuning some of those services that we will be talking about, making sure that they're not just nominally real-time, but like really real-time. So with that, let's get into it. Rafi has all the nicest transitions in slides. So yeah, I am channeling him today. So if I haven't told you that I work for Oracle, you would get a clue. This is the standard disclaimer. Even if this guy lies through his teeth, we don't care. Don't hold it against us. So, all right. We will talk mostly about timeline delivery. When we talk about tweet delivery, it is really all about timelines. Timelines are chronologically reversed ordered series of tweets. And that everybody who uses Twitter, no doubt, knows how does that look like. There are several categories of these. We have so-called targeted timelines. Your home timeline is the typical targeted timeline. When you log on to Twitter, what you see is your home timeline. It's targeted, it's personalized for you. We can get them as pulled timeline. So when you log on to Twitter, what you get, your browser is pulling the timeline down. Or any of the Twitter clients hit twitter.com, you will be interacting with the home timeline API, and you will be pulling your current timeline from there. Aside from this, there is a queried timeline. When you are doing a real-time request into Twitter and you are asking it to search in the overall corpus of the tweets based on keywords, then you are doing what you get. You are getting a query timeline. You are using the search API. When you hit this API with particular parameters, you are causing a search process to go through the system. We'll get to that. And aside from the pull-based tweet delivery, we also have varieties of push-based deliveries, and there is a duality to targeted and queried on the push side. One of those are the user and the site streams. We will cover what exactly do these mean later. And with those, we can deliver timelines to your device without the device having to pull all the time. Normally through an open socket. One of those said user and site streams. The other kind is the so-called track follow, which is sort of like a standing search query. You open a connection to this API, you specify certain set of users or tokens that you're interested in, and those tweets that come in the real time, they match these the criteria that you set, they get pushed to your device. All right, so how does this typically look like? Well, let's talk about a bit of a quick overview of how does Twitter work. People tweet. When they do, they are filling their so-called user timeline. This is a snippet of my user timeline that Raf retrieved a few days ago, and this is particularly funny, right? And so these are some of my tweets as they were happening. Now, if somebody is following myself and maybe Matthias, then you have another set of tweets that Matthias was tweeting. And if somebody is also following JFocus, then you will have another set of tweets that the JFocus account is tweeting. Now, normally, if you follow these three people, what you get is a reverse time-ordered merge of all the tweets of the people you follow. Now, of course, this is not that trivially easy, because the timeline rules are a little bit more complicated. We have @replies, we have retweets, and there are rules for when do you see a retweet. You might see a tweet from somebody you don't follow because somebody who you follow did retweet their tweet. If people are having a threaded conversation using @replies at each other, you only see those if you follow both parties to the conversation. Otherwise, if I respond to a tweet from someone and there is somebody observing me as I'm tweeting, he follows me, but he doesn't follow the person that I @replied to, he won't see that part of the conversation. These are tried and tested rules over the years, and of course they have to manifest themselves in the software. So compositing a merged timeline is not all that trivial. So obviously we cannot really do it all the time on every request because it would be horribly slow. Several years ago when I was actually joining Twitter, I have a friend, and my friend asked me, so how many people work at Twitter? And at that time it was 300. I think right now it's probably more like 1,500 people, something like that. But my friend was actually completely incredulous when he heard the 300. He was like, what could possibly 300 people do there? This is such an easy service. I could write this in an afternoon. And yeah, of course you could, and it would work for you and 5 of your friends. So anyway, let's see how this works. You tweet something. This tweet will hit the so-called write API. It's an HTTP endpoint. We are, of course, highly abstracting the system here. And what happens is that once we hit the write API, we need to ensure that all of your followers will see this tweet, hopefully in something that can be considered real time. What we don't show is that the tweet will first be written to disk, and a quick HTTP response will be returned to the client, so everything is asynchronous, decoupled from there on. We don't want people to have to keep persistent connection when they tweet. We want to return to them a quick HTTP 200 OK as soon as possible, because maybe they are tweeting from a mobile device that wouldn't be too good at maintaining a longer connection and so on. So we try to be nice and quick. We want to return within 50 milliseconds after we eliminated duplicate tweets, because we watch for that and other like trivial business logic in the tweet format of the HTTP request. So what happens after that is what we call a fan out. We call it fan out because we take every incoming tweet and insert it into the home timelines of all the people who are following the author of that tweet. We fan it out into all the home timelines where they need to go. We have a timeline cache, and this timeline cache is based on Redis. Redis is a very nice in-memory key value store. It's sort of like Memcache, except that it allows for Memcache deals in binary blobs. Redis deals in structured data, and this is actually significant for us. But anyway, you can think of it as an in-memory key value store. Now, of course, we don't have a single Redis instance. We have huge bank of Redis instances that are keeping the timeline cache. And in addition to that, for fault tolerance, every person's timeline will not live on a single instance. It lives at 3 instances. So when it has to be retrieved, if for the first machine that you hit for a particular timeline based on some kind of a hashing algorithm, obviously, you don't find it there. You can go around, find it in a second or third instance, hopefully. At Twitter scale, machines just fall over every time. You have to plan for that. It's just part of the business. You never have an assumption that something is up. If you do, your system won't be terribly stable. So what fanout does is we have the social graph service, which maintains the information of who follows who, among other things, and figures out all the people who are following the author of the tweet, and then start the insert process into Redis instances. Fanout itself is not just a single machine, obviously. That's also a bank of machines, and they're interconnected many to many with all the Redises. There's a lot of TCP connections being open at the same time, but that's the way it has to be. So, say Rafi tweets or I tweet, and then we query Redis for, okay, who are the people who follow Rafi? And then we have to append this tweet into each of their timelines. Now, insert into Redis. For every user's home timeline, there is a key in the Redis, key of the recipient, and we will just append to that. It's replicated, and also we are pipelining to about 4K destinations at a time, so we are chunking it into 4,000 followers, push this to Redis at once. Using Redis is nice, and why do I, oh, sorry, just, sorry, my machine is having a senior moment. All right, so as I said, we have a native list structure in Redis, so we can just append one after the other. Back in the day, in the ancient history, probably 4 years ago, I think for a while we tried using memcache for these, and of course it didn't work out after a while, because every time you had to pull in from the memcache the binary blob, that was the timeline, append an element to it, then serialize the whole thing back. With Redis, we just tell it, here's this key, push this element to the list. Since Redis actually knows about data structures, bandwidth-wise, it's just so much nicer. We use the rpushx command, which basically in Redis means, if the key is not there, ignore this command. So we are not doing any work for those people whose timelines are not cached. And whose people's timelines are not cached? Well, people who are inactive. So if you haven't logged into Twitter for a long time, your timeline will eventually fall out from the cache, because Redis is an in-memory thing. If you assign it, 24 gigs of memory on that particular box, then whenever it has to, you can configure it with a policy that whenever it needs to evacuate something from memory because it's just running at full capacity, or just be throwing away the oldest items, so it works as an LRU cache. So what we store normally is ID of the tweet, the user ID, and some additional bits. We are not storing the whole tweet, because that would be hugely redundant, because as same tweet, if I tweet something to my meager 2.5K followers, then you will have to have that stored 2,500 times. If Lady Gaga tweets something, then honestly, I don't even have an idea how many followers she has these days. It's either single-digit millions or double-digit millions, one of the two. So obviously, we don't want to replicate a lot of that. The other thing we do is Redis is really good at storing variable length entries, so there's no need for all of these records to actually be the same length. I mean, Redis is beautiful. I just cannot say enough nice things about it. We really love it. So in case that your tweet is actually not a tweet but a retweet, we can append the ID of the original tweet to your retweet. When you retweet something, you actually behind the scenes you're generating a new tweet with its own ID, but it's linked to whatever was the retweeted one. As I said, we are highly redundant within data center. If you wonder about the cross-data center replication, then we are not doing it on the Redis level. There's just too much bandwidth. There's just too much traffic that would be going on. We actually do the replication on the write API level. So the tweet stream as it comes in the write API is actually replicated to additional data centers, and all the computation is basically repeated in every data center. That's what worked best for Twitter. So, after a while, you want to pull this thing in your browser. What happens is that there exists a thing called the timeline service, which will read these Redises or Red-eye. A tweet is obviously more than an ID. In order to get this nice display, you need to compose it from the user's icon, the text of the tweet, geo-information, whether you favorited this tweet already or not. That all needs to be in the rendered version of the tweet. This is the so-called hydrated tweet, and the timeline service is interacting with other services to hydrate the tweet from the tweet ID that it pulled from Redis. However, the thing is, if you are in cache, this process takes about 50 milliseconds. It's nicely optimized over the years. If you are out of the cache, then what timeline service has to do, so you haven't logged in for Twitter for several weeks, you fell out of the cache, we started updating your timeline with tweets as they come in Redis, then this timeline service will have to hit the social graph service, figure out who you follow, query their timelines, reassemble your home timeline, stick it into Redis, and then carry on. And that takes about 3 seconds, but it only happens for people that were inactive for a time. So this was the basic targeted timeline in a pull mode. Let's talk about search a little bit. Search works somewhat different. The write API also forks off to a thing named ingester, which goes to which tokenizes the tweet, and then we have a search index which runs on a bunch of services named the early bird. At Twitter, everything has to be a bird. Early bird is actually an optimized. Think of it as an optimized Lucene. It mostly is an optimized Lucene. Of course, we have a bunch of those again. However, the significant difference is that while the insert into the Redis fans out, so it's potentially an order n operation based on how many followers you have. This guy here, ingester, it tokenizes the tweet and uses the tokens plus other signal, geoinformation, and so on, and just pushes it into the relevant index in the search index in a particular early bird. And then when you do a search, you are faced with a thing called Blender, which is a quite ingenious piece of engineering that some really, really smart folks in the search organization did. And it does a really nice and quick scatter-gather of all early birds for the index, for all the terms in the search query that you did, applies some more signals from your search. It might figure out who you are, where you are, what were your past interests, and so on. Based on that, re-ranks the results and then does a real-time merge and presents all of that to you. As far as we are concerned, though, the delivery itself from write API until the index, it happens really quickly because we are just inserting into index per token. There's no fan out as such. So you see there's this interesting counterbalance. Redis timeline caching is a little bit, it's expensive on the write, it's cheap on the read. Search is cheap on the write, more expensive on the read. Fortunately, we have a lot more of those than we have of those. All right. Oh yeah. Aside from explicit queries, we also have a kind of an implicit query, which is the Discover tab. Discover tab is basically an implicit query. It also runs off of Blender. As I said, you're logged in, right? So there is probably an information about your geolocation, your past interests, and so on. So it is also used, Blender is also used to compose the Discover tab that's on the far left right now. All right, that's the pull mode. This was the search API. Let's look into push. Very nice transitions here. Yep, repeat. All right, the push cluster. Obviously, we have HTTP push and mobile push. Let's discuss HTTP push first. This is, if you could, like, real time look at the bandwidth that comes in Twitter, you would see something crazy like this. It's a bit like the Matrix, isn't it? This is JSONized tweets. A tweet might be 140 characters, but when you tokenize it, extract the entities, the URLs, the usernames, whatnot, they usually can get up to a few kilobytes of JSON, and this is normally the internal form that they are being trafficked within the Twitter system. We have a service that's called Hostbird, and this maintains persistent connections with the end clients. It is mostly a routing cluster. Right now, for all public tweets, you need about 25 megabytes per second bandwidth to consume all the public tweets. And not just tweets, but also the events. I have to emphasize the events because you'll see why they're interesting, why they're important. So the write API can also hit the Hostbird. Now, Hostbird is, it just gets all the tweets and then it routes them into different queues for public tweets, for social events like people follow, unfollow, delete tweets. These are all additional events that need to be taken into account. They need to be paid attention to in order to have everything consistent and work correctly. SLA is about 150 milliseconds in sending these out, and we need to figure out what to do. Now, the thing is, obviously, you cannot have a single machine for that. At any given time, we have about 1 million clients connecting to the push API. That's 1 million open sockets. No way, there's no hardware right now on the planet that handles this for a single machine. And even if it did, it would be really, really bad for failover, wouldn't it? So, so what there is I mean, structurally it's beautiful, right? It's a cascading cluster. You have one machine, everything comes in, it fans it out to 2 or several other machines the next level, which mostly do nothing but fan them out to another level and another level. And there is 4 levels of cascading in the Hostbird cluster right now, and you can always add a 5th one if people start tweeting 5 as much as they do these days. And that last level is mostly that maintains it's the edge. It maintains the connection with the external clients, with the tweet decks and Twitters for Mac and any other third-party clients of this world. They're running on gigabit Ethernet cards, and they are provisioned for about between 2 and 3 times of the highest observed spike so far. So, you know, there is some additional capacity in the system. There has to be. An interesting tidbit: social graph changes happen 10 times more often than actual tweets. You wouldn't think this is true, but I mean, when I learned that, I was flabbergasted too. But in the Hostbird event stream, the social graph changes actually are 10x to tweets. It's quite amazing. So, what kind of clients do we have on the other hand? Well, we have the fire hose, which is, you have an edge machine, it's just this basically raw input of public tweets, it goes out to it. This is not publicly available. Companies pay for this. Google used to pay for it so that it could real-time index it. Other companies are paying for it. Of course, it's also not publicly available because it's quite costly to maintain. You need to provide a 25 megabyte per second connection to that entity that's purchasing this from you. For And of course, you can only just have a limited number of these per box because it's like a huge bandwidth. That's why it's called fire hose. We used to also have a garden hose. I don't know whether that exists anymore, where you could, without paying, you could subscribe to a fraction, 1% or something like that of the public tweets if you wanted to sample them for research. I'm not sure whether that exists anymore. Rafi, do you know?
Yeah, we still do support it for smaller organizations.
All right. Okay, so this is Firehose. You have the other thing, which is the so-called track follow. Track follow is if you ever use the TweetDeck, then in TweetDeck you can specify, I want to see all the tweets from this user and that user and another user, and additionally all the tweets that mention JFocus or Stockholm, and then you will get a real-time push of those. What happens is that the tweets are tokenized. The edge machine, when you open the connection to this, you're actually sending an HTTP request that has a huge list of parameters saying, these are all the tokens I'm interested in. And then it's doing the filtering and only sending you those tokens that you are interested in. This is Search Lite in a sense that instead of hitting the expensive Blender query API, you are just getting a stream that's filtered on user and content tokens. We might be sending you a little bit more than you originally wanted to get, but this is counteracted by the fact that the client, TweetDeck or whoever, can do some client-side filtering on it additionally, so we don't worry much about that. And there is the user streams, which basically replicates your home timeline experience. You log into the Twitter for Mac or Twitter on your iPhone, and as tweets or tweetbot or whatever, and as tweets are coming in, you are just getting them, right? So it's almost identical to track follow, except that instead of you specifying the search terms, it's basically saying anything tweeted by these people, you will send it out on the socket. So anything tweeted out by your followers, it will be sent out of the, through this socket. And the reason why we have to propagate social graph changes through this cluster as well is that if you start to follow somebody new, then all the edge machines will have to get notified that, hey, this guy is now following somebody new, so yeah, now you will need to stream additional tweets through that connection for that person, for his Mac on iPad. Or you stop following somebody or you blocked somebody, then obviously, again, this needs to be updated. Most of the RAM and CPU in these machines is actually used by maintaining this kind of a cache coherence. Of course, I think we also do something, since we have a lot of these machines, they will do rolling updates of social graph as well. So sometimes they just throw away whatever is cached and refresh from the social graph just for additional consistency. All right, so this is what we covered so far, which is quite a lot. So there is your Twitter for Mac. Basically, when this thing runs, it never hits the pull API, it just goes through push, except when you start it. Because when you start it, if it only used the push API, your Twitter client would start blank, and as people are real-time tweeting, it would start to fill up. But that's bad user experience. You would like to see the tweets that were tweeted several minutes before you launched your client. So in launch Twitter for Mac or iPhone, iPad, whatever, it goes to the timeline service, pulls tweets, backfills its UI, and after that, it only talks to the HTTP push. Well, except if you scroll back a lot, then it again has to talk to the timeline service, but mostly we try to avoid it. All right, we covered almost all of push, except the mobile push. So yeah, let's quickly talk about that. Mobile push is it's somewhat similar to HTTP push, and it's somewhat similar to the Redis fanout. It's an interesting hybrid of the two. Every tweet will hit the mobile push daemons, which are a little bit similar to how fanout works, because the mobile push daemons will also interrogate the social service graph to figure out who do you mobile follow. Now, Twitter actually has more than one follower graph because there is such a thing as follow, and there is such thing as mobile follow. You might be following a lot of people, but you don't necessarily want to be notified in SMS when all of those people tweet. So you can separately specify who are people for whom you might want to get push notifications on iPhone or SMS and so on. So it interrogates for the mobile follow, and to all your mobile followers, then it similarly fans out, except instead of into a timeline cache. This works in a separate data center which has dedicated lines for almost all of the world's mobile phone carriers. It's, when you think about it, it's quite scary, right? But this is what it does. And then, you know, just exerts pressure on them, just sends to their API saying, we have a phone number on file, send this SMS to this phone number, and pushes them. There is usually a bit of a back pressure on that, so when your tweets get dropped, it's most likely not Twitter, more likely AT&T, but let's not shift the blame, but anyway, yes, let's shift the blame, it's them. And yeah, that's pretty much how it works. All right. So the idea is that we actually want to, ideally we would like all computation to happen within 100 milliseconds of a tweet arriving within Twitter. I'm not sure whether we are hitting that goal yet or not, but most of the computation should actually happen. Obviously you have, I mean, a big fan out to Redis will take a while. All right. What else do we have? Okay, this is a recap slide. Oh yeah, we have batch computation. This is not real time, it's included for the sake of completeness. There is a honking big bank of Hadoop clusters which also receive all the right API, run a bunch load of analytics on it. And if you don't log into a Twitter for a day or so, you might actually receive an email from Twitter saying, hey, this is some tweet that we think are interesting and that you might have missed. That's what Hadoop does. Runs analytics and sends you out this email. It knows what you might find interesting only from people you follow, but then it can use a bunch of signals, as in what was interesting to you in the past, what tweets with links from those have people clicked the most. That's why it's good to have a routing URL shortener, for better or worse. And that's what the Hadoop cluster does. This is not real time. It runs nightly right now. I think whenever they can, they will try to make it hourly or even more frequent. Obviously, the more frequent, the better it can service everybody. But right now, I think it runs nightly. So, when we talk about the path, we have the synchronous path, which is hitting the right API. As I said, aside from a little bit of tweet deduplication and similar, it returns really quickly within 50 milliseconds or less, so as to not confuse your device trying to go over a shaky edge connection. And everything after that happens completely asynchronously, completely independent. These three paths happen completely independent of each other, and this is the tweet delivery, and obviously there's a query path for when you go to the website, you query the timeline, and you have the discovery and the search. It's just a quick recap. So, Raf would like us to talk about some things we're trying. Namely, again, you tweet something, and it hits the right API, goes to the ingester, goes to early bids and Redises. One of these things is fairly much like the other, right? So, one side is ingesting into searched indexes. So the tweet will be indexed into the index for the word hello and to the index for the word world. And on the fan out, it will go to the fan out index. So Rafi tweets, then we know that Dana is following him. So we'll need to insert the tweet into Dana's index. So it's all about inserting tweet IDs into indexes. They're really, really similar, right? So we always have a user intent, you have a query expansion, which when you search for hello world, you want to search for the intersection of the indexes hello and the world. On the other hand, when you say, I want Rafi's home timeline, which is right now works from Redis, what you're really saying is, you want this key from the Redis, But this key from the Redis is actually a union of a bunch of others, because if Rafi follows Nelson and Dana, then we will need to actually get a merge of these people's indices. So both of these things are Boolean operations on indices. They are very similar. So there's some thinking on how the hell could we unify these things, right? So, but you also see there's this interesting duality. One is fan in, one is fan out, the other is fan out. One is cheap to write, expensive to read. One is expensive to write, cheap to read. And it works right now because people search less than they update their timeline, so you would think it's fine, except for one little thing. Celebrities. When celebrities tweet, then you might have to update like a few million timelines. That takes time. It introduces unpredictability into the system, and you know, a good system engineer gets nervous when there's unpredictability. So it's hard to capacity plan for that. So you would like to do, you would like less uncertainty in your system. And so how? Well, one thing that can be done is, okay, 10 minutes, excellent, all right. That chimes in with my own timer. And so you could do things where we say, okay, if somebody has a lot of followers, so we have a celebrity threshold, Twitter celebrity threshold, that'd be a nice thing, right? It's like 2 million followers. You have more than 2 million followers, then Twitter will just not fan out your tweets into Redis. Just not. Instead, when somebody wants to pull their timeline and they are following some celebrities, then what we do, we return Rafi's home timeline. So Rafi needs his timeline, we return his timeline into which we've merging all the less followed people. So myself, my tweets would end up in that particular index because I don't have many followers. But Rafi likes Taylor Swift apparently. So and when she tweets, we wouldn't merge Taylor's tweets into Rafi's timeline. Rather, when Rafi retrieves the timeline, we would do a real-time merge of celebrities. So we have a pre-computed, pre-cached partial timeline for lightly followed people, and we have a real-time merge of highly followed people. So writing gets cheaper, reading gets a bit more expensive, depends on where you make your threshold, you can hit a sweet spot with the computation. So that's one of the things that might be thought of as experiment. There's also the question of a streaming compute. This is the generalization of the push infrastructure. Hostbird is a pretty old piece of Twitter infrastructure, but it's not leveraged for any other purposes except for this kind of a light tokenization, delivery, and track and follow, and so on. There is Nathan Martz has his cloud, Storm. It's hard to get up to date with all the weather-based terminology. So he has a Storm continuous computational system written in Clojure. It's actually a really, really nice piece of code. It's available on GitHub, and Twitter is internally, I guess, starting to deliver it for things. You can do things like real-time clickstream analysis for figuring out people's interests, so that in real time you can re-rank search results, because you can quickly notice that something became more popular than something else. It can be used for a lot of things. This is basically a generalization of the push mechanism. You want to do more computation on the write pass, and end up with hopefully less disk and memory usage on the read pass. So these are some of the things that we're trying. Okay, recap of the full system, and we'll finish with some timeline statistics. Twitter has about 150 million active users worldwide. You get about 300,000 poll-based timeline requests per second. That's quite a lot. The 50th percentile for satisfying this lookup is 1 millisecond. That's amazing. 99% is 4 milliseconds. Typically, 1 millisecond is for the Redis lookup itself. The rest of the latencies goes to the composition. There's also like 30K queries per second for the search-based timelines. And what we have on the input side is about 340 million tweets a day and growing. Average is 4K, peak is about 6K daily. So you have large events that can jump up to 10 for a little bit. Now, the thing is, these numbers are actually not particularly impressive on their own. You might think they are, they're not. We'll get to the impressive numbers. So, this is a change in a Twitter traffic over time. This is one day. This is the average. As you can see, the system is actually running quite a lot above average, which on its own, this doesn't really mean anything. But you have to plan for that. The pattern is closely correlated, obviously, with when is the sun mostly up above regions where people tweet a lot. However, what is interesting is that when Dana tweets or Rafi tweets, they follow each other. They will see each other's tweets. But as soon as you add more people in the mix, every tweet that's tweeted, every single one of those 340 million tweets per day are delivered to many other people. So that's why it's not so much about 340 million tweets a day, okay, whatever. But this means 26 billion deliveries of tweets a day, because each tweet has to be delivered to many people. It's like 18 million per minute. You get that down to, I don't know what was that in seconds, but it's, oh yeah, it's there. It's 300,000 deliveries per second. It's a lot. That's so many times a tweet is inserted into Redis, a tweet is pushed through a hostbird cluster, a tweet will ring somebody's phone. That's 300,000 times per second. Now that is an impressive number, and there's an infrastructure that handles that. So the real motivating factor for why do we want to do this, I don't know how do you see it. This is immediately after following the Japan earthquake, you see the flow of the tweets. As the earthquake hit, as you had the global replies. And this is why you need real-time delivery. This is what differentiates data from information. Information is something that has value for people at the time it is delivered. Twitter delivers information faster these days than anything else on the planet. There's this, when that plane landed in Hudson, the New York Times people, journalists, were watching it from their windows, and they knew they cannot publish it for several hours until they go to print. But it was on Twitter. And most recently, well, not most recently, fortunately it has been for a while now, but the example that Rafis here had on the video, many of those tweets going in and out from Japan were tweets about people giving a sign telling I'm fine, and other people asking, are you fine? Conversation is also real-time, and being able to have a real-time two-way conversation, or just give a sign. I mean, just think about it, most basic thing. Give a sign that you're alive in the time of trouble. Now that's a big thing. That's why real-time delivery matters. And with that, that's all I had to say. Thank you.